Let's do the weight versus mass lab. Let me introduce a few concepts to you and review some concepts that we talked about before. So this will be the intro. Okay, we're familiar with the word weight. Here's something that has weight. Okay, this is actually a 500, you read that, it's a 500 gram mass. Of course, we use kilograms in here, so 500 grams, what is that in kilograms? Kilo means 1,000 grams, so this is about half of 1,000 kilograms, this is half a kilogram. And if I hold it in my hand, like this, it definitely has weight. So what I want to do is talk about some of the things I talked about before when I'm just doing something super simple like this. Pay attention, please. I'm just holding this with my hand like this. So what I want to do is draw an interaction diagram for this, and then we'll talk about the difference between mass and weight. So here's the here's a little picture of the 500 gram mass. Okay, and here's the ground, also known as the earth. And these two objects, the earth and this 500 gram mass, are interacting. That is, they're applying forces to each other. Now, Sir Isaac Newton figured out a mathematical model, a mathematical pattern that described how two massive objects apply forces to each other. But he didn't know why. He famously said, "I feign no hypothesis." I don't know why the earth and the moon are attracted to each other. I don't know why apples fall from trees. I don't know why there's an attractive force like that. I just know that there is, and this is the equation that describes it. And we're actually going to study that equation later on, Newton's law of gravity. But for right now, it's good enough to say this. The earth pulls down on the mass, and we call that the force of gravity. Of course, there's an equal and opposite force applied to the earth. The earth pulls down on the mass, but the mass pulls up on the earth. So how come we don't see the earth rushing up towards the mass? Because the earth is huge. The earth is so big. I can tell you how big the earth is. The earth has a mass of, you don't really even need to write this down, but it has a mass of 5.98 times 10 to the 24 kilograms. Now 5.98, that's pretty close to 6. Now 10 to the 24, well, what is 10 to the 12? 10 to the 12 is a trillion. So this is 6 trillion kilograms. How big is that? I don't know. I just know it's so big I can't even imagine how much mass that is. So this weak, puny little force that this 500 gram mass is pulling up on the earth with is not going to have any noticeable, any measurable effect on the earth. Okay? Now you all have mass. Okay? So believe it or not, right now, this very second, you're all gravitationally attracted to each other. Gravitationally attracted. Okay. Yeah, get away. Okay, for whatever other kind of attraction, that's up to you. Okay, I'm not going to get into it. This is not a biology class. This is a physics class. But there is a gravitational attraction. However, gravity is a very, very, very weak force of nature. And that force is not strong enough for everyday size objects or person-sized objects to notice it. Even if you have a mountain, if you were standing next to a mountain, you know, at the base of a mountain, you would think that the gravity of the mountain would pull you up the mountain. Well, there is a measurable gravitational force between you and the mountain. If you had the right instruments, you could detect it, but you're not going to notice it. It's still overwhelmed by the gravitational attractive force of the earth below your feet. So the force of gravity is a force that pulls massive objects together. Now, I'm also holding it with my hand. Now, drawing a hand is kind of difficult, but I'll give it a shot here. So this is like the thumb, and here's the, not very good. So I'm trying to draw a hand here. Looks more like an alien's hand, I don't know. All right, but anyway, so we're holding the mass. I mean, what would happen if I didn't hold the mass with my hand? Yeah, gravity would pull it to the ground, but instead I'm holding it up. So my hand applies a force to the mass. I'm going to call that an applied force. We could also call it a normal force or something like that if we wanted to. But remember that the mass applies an equal and opposite force to my hand, right? The weight that I feel right now is I feel this massive object pushing down on my hand. So this is the force on my hand applied by that mass. Well, what do I really want to do, though? I want to take a look at just the mass. So what did I draw? Well, remember in the videos I talked about this? This is the interaction diagram. I'm showing the interaction between the mass in the earth and the mass in my hand. But I only want to look at the massive object itself. So I separate it and draw what's called a free body diagram. Over the next 2 weeks, we are really going to study how to draw a free body diagram. A lot of my students go to college and study, my former students go to college and study engineering. And the number one feedback I get back from my students is, thank you for teaching us free body diagrams. If you're going to go into engineering, free body diagrams is your bread and butter. I mean, they do it all the time. So what is a free body diagram? Well, you take the object and you just draw the object and the force is acting on it. So here's my 500 gram mass. And I draw the forces acting on it. Here's the force of gravity. Here's my applied force. Now, I'm going to say that up is positive. I'm going to call it positive y. This is the y direction. And once you've correctly drawn a free body diagram, you can now use Newton's second law, which was covered in the video on Friday that you watched while I was out at the CSTA conference. And what is Newton's second law? Newton said, hey, the result of applying a net force to an object is to make that object accelerate. What causes accelerations? Why do objects accelerate? Because something is compelling them to do so. Something is pushing or pulling on them and making them change their motion. Objects don't want to change their motion all by themselves. An outside force has to be exerted, a push or a pull. Has to be exerted. So this net force causes an acceleration. The amount of acceleration depends on how much stuff you're trying to accelerate, right? I mean, this makes sense. an object with a lot of mass, it's hard to make it accelerate, isn't it? It's hard to push on it to change its motion. So the net force is equal to an object's mass times its acceleration. This is Newton's second law. Hey, folks, this is the most important equation in all of physics, right here. If you understand Newton's second law, it just unlocks the universe to our minds. It is no coincidence that the Industrial Revolution occurred shortly after Newton published these results, his laws of motion, particularly his second law, which is expressed by this equation. Before Newton did that, people were inventing technology, but they were inventors, they were tinkerers, they were craftsmen, but they weren't engineers. This allows us to do engineering. And once we started using these laws of nature that Newton discovered and pointed out to us, we could start inventing technology that led to the world we have today and is going to lead to the world we're going to have tomorrow, which I hope is better than what we have now, because we're kind of screwing it up now, if you ask me. Now, what is the net force? The net force is the force you get when you add up all the other forces acting on the object. Well, look at my object. I have to add these forces together, but what kind of quantity is a force? It has magnitude and it has direction. So therefore, force is a vector quantity. And so I'm going to add these, I add all the forces acting on an object together. Now there is a symbol that means, hey, add up all this stuff. You remember in Algebra 2? You learned it. It's a plus sign, sure. We are going to use a plus sign, but it's the sigma, right? Capital sigma. The summation sign. Remember that? There's summation notation. We're not going to mess with all the summation notation. This just means, hey, add up all the forces. This is how I'm going to write Newton's second law from now on. If I add up all the forces acting on the object, it will be equal to the object's mass times its acceleration. Now, using this equation to define what a force is, let's look at the units. Kilograms, meters per second squared. And what did I say last time that a kilogram times a meter per second squared was equal to? It's a Newton. Wow, that was unnecessary. All right. It's a Newton. It's ooey gooey, rich and chewy inside, and golden, flaky, tender, cakey outside. Is that right? No, that's not named after the scientist. Fig Newtons are not named after Isaac Newton. That's what I've heard. I don't know. We'll have to look it up on Wikipedia. All right. Now here's the point of this. Now please listen. If I'm just holding this mass in my hand, is this mass accelerating? Look at it. No. It's at rest and it's remaining at rest. There is no acceleration. And so the acceleration is 0. So if I add these forces together, they have to add up to be 0. So I'm going to do this. This is in the positive direction, my applied force. And this is in the negative direction. So instead of going plus negative, I'm just going to say minus. So the applied force minus the force of gravity is going to be equal to 0. Now, what does this allow me to say? I mean, it's pretty basic. The applied force, that is the supporting force my hand is providing to that mass, is just going to be equal to the force that the Earth pulls down on it, which we call weight, or the force of gravity. So that was the point of all this. So, look, if I take this 500 gram mass with me to the moon, and I'd love to be able to do that, but if I could take this with me to the moon, is there going to be less stuff? Is there less mass? No. The mass doesn't change. It's still the same amount of stuff. But does the weight change? Yeah, it's going to feel much lighter. Why? Because the moon is tiny compared to the Earth. The moon only has about 1/100th as much mass as the Earth, and therefore, the radius is smaller too, and we'll get to those equations later on. But it turns out that stuff on the moon only weighs about 1/6 as much as it weighs on the Earth. So what we want to know is, what's the relationship here on the Earth? What's the relationship between the mass of an object, how much inertia it has, what its resistance is to acceleration? Or in chemistry, you learned that mass was the amount of protons, neutrons, and electrons. You have how much stuff, how much matter you have, which is a perfectly good way of defining what mass is. What's the relationship between weight and mass? So this is our question for today's lab. Okay. How does weight, and we're going to use F sub g to represent weight. What does F sub g stand for? Force of gravity. Weight is the force of gravity. How does weight depend on mass? Now, mass, we're going to use the letter m to represent mass. Lowercase m is the accepted variable for mass. Now, this is for here at the surface of the Earth. Okay? Go somewhere else in the universe, it's going to be different. But it's hard to get to anywhere else in the universe, so this is going to be good for the rest of your life, probably, unless you become an astronaut, which would be awesome. Okay. Now, how are we going to measure this? Well, we can't measure weight directly, but what we can do is hold the mass up with a spring scale. Okay, so we're going to take here's the mass, and we're going to hook up one of these on it, a spring scale. And we're going to hook the mass on here, and we're going to hold it up. Zoom all the way out so everyone can see what I'm doing. Of course, I have this laid out on the table, but you're gonna hold it, up and down, and you're gonna measure the mass. Well, you're gonna measure the weight. I'm sorry, because the upward force applied to the upward force applied by the spring scale has to be equal to the weight if the object's going to be held in equilibrium in front of your face. Okay, I'm going to hold it up like this. Okay. And what I can do is measure, along here, figure out what its weight is in newtons. Okay, now, one thing about using a spring scale, you have to zero it first. Now, if I look right here, let me zoom in. See this right here? Where should this be? Should start at 0. So start at 0, like that. You just put all your stuff right there in the corner. Now, where are you going to make 0? Is it going to be at the top of the tab, at the bottom of the tab, in the middle of the tab? I don't care as long as you stay consistent. Now, when you measure the weight of this, you're making my whole table wiggle, man, and I'm recording this. The whole thing. It was Gerardo. Gerardo did it. Okay. So when you put it on there, the weight's going to pull it down. Now I want you to measure the weight to the nearest tenth of a newton. So look at this scale right now. Tell me what weight, if this it starts at 0, so we'll put 0 right in the middle of the tab. So look right in the middle of the tab, it's at 0. What weight is that in newtons? Not dimes, in newtons. 6 point what? Yeah, about 6.2, 6.25. Measure it to the nearest tenth of a newton. Now here's what I'm gonna give you time to do this. You'll have enough time. In order to answer this question, we're going to measure the weight, and we're going to assume that on these guys, let me put it under the camera here, that these guys are accurate, and they are. This is a 200 gram mass, which is 0.2 kilograms. This is a 500 gram mass, it's 0.5 kilograms. This is 1 kilogram or 1,000 grams, right? And we're going to weigh them. We're going to measure their weight using the spring scales. And you're going to have a data table. So let's take some data. And the data should help us answer the question. First thing you're going to record is the mass in kilograms. Then you're going to measure the weight, which we're going to call the force of gravity, and measure it in newtons. Now, let's just assume if you have 0 mass, what's your weight? 0. No mass, no weight. Then you're going to measure like 5 or 6 of them. The greatest mass I want you to measure is 2.00 kilograms. Don't go greater than 2 kilograms because it'll overwhelm the scale. You can actually break the spring scale if you go more than that. What's the smallest mass I want you to use? It's this guy right here. Right here. The 200 gram. Don't go less than 200 grams. So the first one will be 0. Now 200 grams is 0.200 kilograms. So measure its weight to the nearest tenth of a newton. It'll be blank dot blank. I want the nearest tenth of a newton. Make sure your scale is zeroed before, and you have to hang it, up and down like this to make sure that the tab starts at 0. So you have to be very, very precise, very careful. Then what you can do is you can take these, and these are called hooked masses because you can hook them together. So here's 0.5. 0.5 plus 0.2 is 0.7. So if I have this right here, I've got 0.7 kilograms. And you can hook a whole bunch of them up together. Okay, but so I'll let you put whatever mass you want in between 0.2 and 2. Should be in between. Measure their weight in newtons to the nearest tenth of a newton. When you're done with that, I want you to do the analysis. And here's what the analysis will look like. Okay, the analysis force of gravity in newtons, mass in kilograms. I want you to graph it. Now guess what? This is going to be a straight line. So I want you to create a mathematical model that expresses the force of gravity as a function of the mass. Now remember, y equals mx plus b. So what's your vertical axis? Equals what's your slope, what's your horizontal axis, and what's your y-intercept. Create a mathematical model that will express to us how the force of gravity or the weight depends upon the mass. And that's what I want you to do right now. So good luck.